Welcome to this lecture series in group theory. We will continue our discussion on Sylow's theorems, and the topic of today's lecture is Sylow Conjugation theorem, amongst other things. And let us recall two things that we need for this lecture. So we need the notion of the coset action, which we have seen several times, so I'll be very brief. So if G is a group and H is a subgroup of G, and G acts on then G acts on the set of all the left cosets of H in this very natural way. So that's coset action, and let us also recall the definition of a p subgroup. So if little p is a prime, then a p subgroup of a group G is a subgroup H of G such that the cardinality of H is a power of P. Alright, here is one problem for practice, and let us get started. So fix a finite group G and let little p be a prime, and let capital P be a p subgroup of G and Q be a Sylow p subgroup of G. So with all that, we show that there is some group element such that the corresponding conjugate of Q contains P. It's a pretty remarkable theorem and has a beautiful proof. So here is how it goes. So we consider the coset action of G on G mod Q, but we will not work with this action, we will work with the restriction. So since G acts on G mod Q, any subgroup of G also acts on G mod Q, and hence in particular the group capital P acts on G mod Q. Right, so throughout this proof we will work with this action. And now here is the main observation. Since this is not divisible by P, why is that? This is not divisible by little p because Q is a Sylow p subgroup of G. Okay, so since this is not divisible by P, there is a p orbit. So when I say p orbit, this is capital P. When I say p orbit, I mean orbit under this action. So this p is just to emphasize that we are working with this action. So there is a p orbit O such that the cardinality of the orbit is not divisible by P. So why is that? So we first noticed that yes, that this is not divisible by P, that we justified. Now use the fact that this is partitioned by P orbits. If a group acts on a set, the set is partitioned by the orbits of the action. So this is partitioned by G orbits, and if every orbit had its size divisible by little p, then the entire set would have its size divisible by p, and that would be a contradiction. So we have this conclusion. And now since O is an orbit, so since O is an orbit, there exists X in G such that O is all the translates of X by elements of P. Translates of XQ by elements of P. Right, that's immediately from the definition of an orbit. If O is a P orbit, there is an element here whose all of its translates by elements of capital P constitute that orbit. So what are the elements here? The elements here are cosets of Q. So there is some group element such that the corresponding coset of Q, if you translate by elements of P, you get the entire orbit O. So there is such a group element. And now, by the orbit stabilizer theorem, the size of the orbit is the index of the stabilizer of XQ. Right, so this is the orbit stabilizer theorem because this O is nothing but the orbit of XQ, right? That's how XQ was chosen. So orbit stabilizer theorem says that the size of the orbit is same as the index of the stabilizer of the element whose orbit we are considering. All right, but now here is the final main observation, that this is not divisible by P, but this is a prime power, meaning this is a power of P. When I say prime power, I meant a power of little p. Why is that? Well, this is a P subgroup, so this is a power of P. And this is a subgroup of capital P, therefore this whole thing is also a power of P by Lagrange's theorem. And since this is not divisible by P, the only possibility is that this is actually equal to P to the power 0. This is the trivial power of P, because if this were not P to the power 0, it would be some P to the power K for K greater than 0. And this would then be divisible by P, contradicting that this is not divisible by P. So this is actually equal to 1. This is a conclusion because of the fact that capital P is a P subgroup. Okay, and what that means is, that this is equal to stabilizer. All right, which means that gxq equals xq for all g in P, right? Because what does this say? This says that every element of capital P stabilizes that, and therefore we have that, which gives x inverse gx belongs to Q for all g in P, which gives g belongs to xqx inverse for all g belongs to P, which gives P is contained in that, and that's it. It's a beautiful, beautiful proof, and it has some very nice consequences. So this is an immediate consequence of the previous thing. This is called the Sylow Conjugation theorem. So it says that if G is a finite group and P is a prime, then any two Sylow P subgroups of G are conjugate. So this is simply because let P and Q be Sylow P subgroups. By the previous theorem, there exists some group element such that P is contained in X QX inverse, but the size of this and the size of that are the same because P and Q are Sylow P subgroups. So this implies that P is equal to X QX inverse, and therefore P and Q are conjugate. That is the definition of conjugacy. Right? So it's a non-trivial fact, but it's a corollary of the previous non-trivial fact. Okay. And now here is one of the classical results, if you can find it in any textbook, is the following. So okay, give me a second. So let G be a finite group and P be a prime, and let this denote the number of all the Sylow P subgroups of G. So then we are saying that this number is actually the index of the normalizer of any Sylow P subgroup Q of G. So how do you find this number? You find any Sylow P subgroup of G, call it Q, and take the index of the normalizer of that element. Now I'm not saying that this is an effective way to find this number, but whatever. In particular, this says that this number divides G because this number divides G. So it's not saying. It's something interesting. All right. So here is how we do it. So let script S or fancy S be the set of all Sylow P subgroups. All Sylow P subgroups of G. And define an action of G on fancy S as G dot Q is equal to GQG inverse. And you can check that this is indeed an action. Let me not do that check. Right? So it just takes a Sylow P subgroup to its corresponding conjugate. That's how it acts. And here is the main observation. This action is transitive. So this action is transitive. Why is it transitive? It is transitive because of the previous proposition. This is as good as saying that this action is transitive. That's all that is saying actually. All right, so therefore this has only one orbit. That's what transitivity means. And thus, so fix some Q in script S. Thus orbit of Q is fancy S, and therefore by the orbit stabilizer theorem, fancy S is the index of the stabilizer of Q immediately from the orbit stabilizer theorem. But what is stabilizer of Q? Stabilizer of Q is all those things in G such that G dot Q is equal to Q, which is by definition all the elements of G such that GQG inverse is equal to Q, which by definition is the normalizer of Q. That's the definition of the normalizer. And now if you just combine this and that, we see that size of S, which is nothing but NPG by definition, is equal to the index of the normalizer. Wonderful. Okay, So one last piece. So if G is a finite abelian group and P is a prime, then G has exactly one Sylow P subgroup. This is immediately from the fact that any two Sylow P subgroups are conjugate. So if you had two different Sylow P subgroups P and Q, then P would be equal to x, Q, x inverse for some x. But since the group is abelian, this is equal to Q. So if you pick two Sylow subgroups P and Q, you end up showing that P is equal to Q and you're done. So there's no point writing all that down. There is more. I think this is the last thing. So this is called the Sylow extension theorem. It says that suppose we have a finite group G, P is a prime, capital P is a P subgroup of G. Then there is a Sylow P subgroup of G which contains P. So we have a P subgroup. The theorem says that there is some Sylow P subgroup which contains P. So you can kind of extend a P subgroup to a Sylow P subgroup. That's what it does. And this is also clear because so here is the proof. Let Q be a Sylow P subgroup. Of G. We know that there exists some group element such that P is contained in x, Q, x inverse. But then this is a Sylow P subgroup of G. Right? Since Q is a subgroup, this is also a subgroup. And since Q is a Sylow P subgroup, this is a Sylow P subgroup. So P is contained in a Sylow P subgroup. That's it. So the main theorem implies the Sylow extension theorem as well as the Sylow conjugation theorem immediately, amongst other things. Okay, so that's all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.